Hi, this is Yijia from Origo, and thanks for interest in Origo. And this is the second day for Origo's white paper go through. Thanks for listening. And today I will go through the scope of Origo and some design principle, like say how we generate this idea and how to like say okay, let's implement this idea. Try to implement some of the idea like to on Ethereum and what's the limitation of like say current solution to protect part of the privacy. Okay, so let's steer like go through about the privacy problem we mentioned yesterday, so you can remember some of them. I say currently like a contract, there are lots of like real world contract like has sensitive data details, and Ethereum is fair to like protect those privacy, which restricting the usage, right? So Origo scope is different than like Monero or Zcash. They are building pretty good, and they enable the private transaction for people, so which can protect sender's address, protect the transaction amount, and protect the receiver's address. And Origo is trying to build up something like besides the private transaction, we're trying to enable the protection for like applications inputs and applications outputs. So the way that Monero and Zcash they implement like to the tool they use, or the design they use for only doing the private transaction is not like we cannot use that directly, because that's not fitting the functions. So Origo's design will be a little complicated than them, and then so it's totally different. That's our scope, and so our design principle, like say how to generate this idea, what we want to ensure to the user, is like think about the smart contract. We need to prove like to protect the privacy of the inputs and outputs. Usually, like people doing like a smart contract, it's like okay, they put the input data on Ethereum, so all of the nodes can like getting those inputs can run it again to getting the outputs. So all of the inputs are like public. So in order to like say keeping this privacy of the inputs, there are two methods. One method is like say okay, I put a commitment. So I will explain what is commitment. Commitment is something like say for voting for Trump, and then I just like submit a hash of Trump to the blockchain. And so other people know, okay, this is like a random hash, and I don't know what's the content back of the hash. So that's like a commitment. I commit something, and then you don't know, and I can provide the stuff to prove, okay, this is the hash of the choice I choose for, like yeah, Trump or whatever, and then that's a commitment. And so the other way is like we don't like store data directly on chain. We only like if we want to store data on chain, it should be encrypted. Like the way to protect inputs. If you don't want to protect the privacy, you can definitely like store it directly. But that's the way to like protect the inputs. You can only like sending the data encrypted, and then people cannot decrypt it. In this way that the privacy can get like protected, right? And so this is the first design principle. We need to guarantee the privacy of inputs and outputs. We can use like a commitment or like encrypted data, but yeah. And the other stuff is the principle is like we need to guarantee the fairness of the execution. I think usually people not like think about the fairness of the smart contract, but sometimes you think about it's a game, it's a poker game, so the privacy is not enough to only say against public, because all of your participants you against each other. So participants may know others' inputs and then abort the contract. Say, okay, you commit. So if you play a poker game, and then you open your cards, you open the cards on the blockchain, and people know, okay, you are really, really big, and then definitely I will lose. Then definitely, okay, I will abort the contract. I won't attend. So in this way, the fairness is not like a guaranteed, because people always know your card, and then if I like will lose, I will definitely like abort, right? Then in this way, the fairness of the execution is not like guaranteed. And the third principle is like we need to guarantee the correctness of the execution, because usually like that's the same for like Ethereum. Ethereum need to guarantee the correctness by like all of the other nodes can validate, can like run this smart contract again to make a consensus to say, okay, this execution is definitely correct. So the way we do is like we need to provide a verifiable proof, like say if and only if the correctness of the execution. If the execution is wrong, then you cannot generate this kind of proof that other people can verify. So it's like it's definitely need to be true, and then people can verify. Otherwise, okay, I don't believe your proof, and then your proof is wrong, right? So that's the design principle. We need to guarantee the privacy and guarantee all of the member participant in the execution need to be fair. So the game need to be fair. The contract need to be fair for everybody participants. And then we need to guarantee the correctness of the execution. So the result should be true, and the result should be correct after the execution, right? So this is the design principles. And let's talk about like how to like think about the solution, like based on this kind of principle, and then on like a current Ethereum. Let's like go through a rock paper scissors game. So rock paper scissors game, I think everybody knows that, right? Just two participants, and then against each other, and then they can choose rock, paper, or scissors, right? Everybody knows that. So think about current state on Ethereum. You cannot like writing simple like that. Then I will explain. So you can say, okay, user A post a choice. Okay, I post a choice for rock, and then user B can, because all of the data on Ethereum is like public, so user B can read the choice, can find out that transaction and read the data, and then okay, can find out, okay, user A posts a rock, and then I will choose paper, and then I will definitely win, right? So this is, so if you write like a rock paper scissors game like that, simple on Ethereum, it won't work, because the user the user, I mean, submit their choice later, then always will win the game. How to solve that? Is that solvable? Yes, it is solvable. So it's like, so we divide the program into 3 steps. So the first step is like you commit. So user A posts a commitment, which is a post his choice, maybe like a rock, with some random string that A knows that. So A can like choose whatever string. I mean, A knows that, and then put them together and generate a hash, and then post that hash to the blockchain. So so user B, which can like post later, they can read the input data, but that's a hash. So user B doesn't know, okay, what's A's input. So same as B is like within this step 1, B need to post the same like a commitment, which is another hash of the choice with some like random string that B knows. And then when A and B are commits, already like post a commitment, then they need to, that's the second step, which is open. In this step, or like after commit, no one can actually change their commitment. So let's say even A open and tell B, okay, my choice is rock. B cannot change the commitment because because that's the second step, that's the open. So user A opened the commit, like say, by like providing the choice and the random string, because that's the hash of the choice and the random string that A knows. So if A want to generate another, say, generate another like when A post the commitment, it's a rock, and A want to like open with a paper. It's really hard. It's like impossible. I mean, extremely hard and impossible. It's like it's pretty hard for A to generate another hash with the same with paper and another random string. So A can only like open this by providing choice and random string, so which can prove to all of the people, say, okay, this is definitely my choice. My choice is rock. Same as B is like a B, maybe B choose paper or Caesar, and then B open the commits, and then with the random string and the choice, so which can matching the commitment, the hash they commit to the chain, right? So that's the second step. They open it, and then the third step is like when they open it, then the blockchain then the logic can decide, okay, which is the owner. So this looks perfect. It's like, okay, this step, the step one, you commit the choice, and you cannot change any more after the commit. So, and the second step, user open it. So the third step, we can decide which is the owner. Any problems about that? Yes. So the fairness get ensured. It cannot say, okay, B, if even B like submit his choice later than A, because when he submitted, he can only see A's commitment. So B cannot like offer anything to definitely win A. So in this way, fairness get ensured, but there's no privacy. You may say, okay, there is privacy. When I commit, then that's a commitment, and then nobody knows my choice, right? But think about step 3. When you settle, when you open, when the logic decide the winner, your choice is still public, and people can see your choice. So all of the other on the blockchain can see the choice and know the winner. So there's no privacy. It can guarantee the fairness. It can guarantee the privacy, like say before open. But when you open and settle, there's no privacy. So it somehow guarantee the fairness, but there's no, cannot guarantee the privacy. So so this is the problem for like current solutions, and so we trying to solve is like say, okay, we can not only guarantee the fairness, but also provide the privacy. You may interest on how we do that. I can explain a little here today, and then I'll talk about the detail tomorrow. So you think about, okay, how to do that? How to keep the data private? So definitely, so the problem is for the step 3, right? So how to make it private is how to do the step 3. So how to do the step 2 and step 3. So you don't want the data to be to rightly open on chain, and you do the calculation on chain. So because you do that, it's like so all of the inputs will be public. So Origo, we do it off chain. So that's the basic idea how we think about and how we do that. And then I will explain our protocol tomorrow, so you know like how we do it off chain and how we guarantee the fairness, and there's no people can cheating and those stuff in the following days. And I'm thinking about it's like not all of the people have knowledge about zero knowledge proofs, so maybe I will like maybe have one day only like talk about like zero knowledge proof with like simple examples. There's no math. I just want to explain, okay, what is zero knowledge proof, and what it can do. So maybe that's some background logic will help people. But I haven't decided what's the sequence. Maybe I will introduce a protocol first, and then before we go into detail, I will explain zero knowledge proof, or I can talk about zero knowledge proof first, and then go through about the protocol. Yeah. Thanks for listening for today, and feel free to have any comments, and I will address that later. Thanks.